What is ammonia? Arrhenius' theory of acid and base, 1887, states that acid is a substance that dissociates in water to form hydrogen ion. Base, on the other hand, dissociates in water to form hydroxide ion. However, there are limitations to Arrhenius' theory of acid and base because the definition cannot explain why ammonia has basic properties. Ammonia cannot be defined because it reacts with acid in neutralization reaction, but it does not form hydroxide ion. Also, the reaction with ammonia can happen without any liquid solvent, just like it is shown in the example below. Later, Bronsted-Lowry theory was developed in 1923, and it is the theory where it recognized the acid-base reactions as chemical equilibrium. Bronsted-Lowry theory states that acid is a substance of which the proton can be removed, which is described as a proton donor. Base is a substance of which the proton is accepted, and it is named proton acceptors. This definition definitely shows why ammonia is basic. Just before we go on any further, conjugate acid-base pair means that a pair which an acid and base that is different by one proton. For example, HCl, hydrochloric acid, and H3O+, hydromium ion, is conjugate acid-base pair from its reaction with water. This is the diagram of the dissociation of ammonia in water. As you can see, the diagram shows us the transfer of hydrogen ion from the water to ammonia. As the definition of Bronsted-Lowry theory said, by ammonia accepting the hydrogen ion, it is the same as receiving the proton, which is making it a base. Therefore, the product, ammonia, becomes the conjugate acid of this reaction. The conjugate acid-base pair for the dissociation of ammonia are ammonia and ammonium, and water and hydroxide ion. Overall, ammonia is a weak base, and it cannot be defined by using the statement that was given from the Arrhenius acid and base theory, since ammonia does not dissociate in water to form hydroxide ion, and it does not have to react with liquid solvent. However, it can be defined under the Bronsted-Lowry theory, where it explains that ammonia is the proton acceptor, which is also called a base. There are many uses of ammonia in the society. It is used in polymers, explosives, cleaning products, pharmaceuticals, rubber stabilizers, and refrigeration. More than 80% of the produced ammonia is used to make fertilizers. Ammonia can also be used in the farm, water, and wastewater treatment, stack emission control systems, pulp and paper industry, and leather industry. Haber process. Before World War I, bird dropping in Peru and sodium nitrate from Chile was the main source of nitrates for human use, and the source was expensive and it was becoming scarce. Therefore, they needed more reliable, cost-effective supply of ammonia. Fritz Haber, who is the founder of this process, knew that ammonia can be converted to nitrates and other nitrogen compounds. Haber process uses medium temperature, which is 500 degrees Celsius, high pressure 2200 kPa to 3400 kPa, and catalyst. In the past, Haber used osmium and ruthenium as the catalyst for this process. Currently, the factories are most likely to use iron oxide, which is cheap and is easy to find. At the end, the process will produce ammonia with a yield of 10 to 20%. This diagram shows the steps that are in the Haber process. When Haber process begins, ammonia is removed by the cooling of the gas mixture, which causes it to condense into a liquid while nitrogen and hydrogen remains as gas. Also, nitrogen is removed during the shift in the equilibrium, which causes it to provide more production in making ammonia. When Haber process is used, it is a must to know about Le Chatelier's principle. This principle states that a dynamic equilibrium tends to respond so as to relieve the effect of any change in the conditions that affect the equilibrium. Also, equilibrium is opposing changes to a closed chemical system occur simultaneously at the same rate. The equilibrium system changes due to many factors that are concentration of the substances, temperature, common ion effect, pressure/volume, and catalysts. Concentration. If the product of Haber process is removed from the system, which is ammonia, then more products must form to return the system to form equilibrium. In other words, the reaction is shifting to the left. If the reactant of the Haber process is removed from the system, which is nitrate, then more reactants must form to relieve the change. In other words, the reaction is shifting to the right. There are three relationships between the reaction quotient, QC, and the equilibrium constant, Kc. When Qc is smaller than Kc, the reaction will be shifting to the left. When Qc equals to Kc, then the reaction is at equilibrium. If Qc is bigger than Kc, then the reaction is shifting to the right. Temperature. The reaction of Haber process is exothermic. This reaction releases heat as the reaction proceeds, which is why ammonia synthesis is too slow at low temperatures. If the temperature was increased in exothermic reaction, then it will decrease the effect of equilibrium constant, which will cause the equilibrium to shift toward the reactants. Pressure/volume. If the number of mole of reactants and products are same, then there is no effect on the equilibrium state of the reaction. If the number of mole for reactants are smaller than the number of mole of the products, and if the volume was decreased, then the equation will shift towards reactants. If the volume was increased, then the equation will shift towards products. If the number of mole for reactants are bigger than the products, and if the volume was decreased, the equation will shift toward products. But if the volume increased, it will shift towards reactants. For the Haber process, it is the scenario where the number of mole of reactants are bigger than its products, and the pressure that the process is happening is really high. Since pressure and volume is inversely proportional to each other, it is right to say that the volume is decreasing for this Haber process, which causes the reaction to shift towards products, making more ammonia. Catalyst. Catalyst is a substance that increases the rate of reaction and is regenerated at the end of the reaction. Haber process uses iron oxide, osmium, ruthenium as its catalyst for the reaction. If this catalyst were used, then they will raise the rate of the reaction, causing the NH3 to be produced faster. By using the catalyst, it shows us that time will be saved and large quantities of ammonia can be made. Overall, ammonia is a weak base, and it is frequently used in the society for many purposes. Moreover, Haber process is a method that uses minimal cost but produces large quantities of ammonia. Some of the illustrative principles that was used in Haber's process were temperature, pressure, and catalyst. Thank you.